right, let's get started. So, good morning, everybody. Welcome. Very nice of you to be here today. For this talk, well, this is not technically a chess timer talk. I'm actually okay to have some interactivity, so if you have a question or a remark in the middle of things, just raise your hand, maybe I'll see you. So before we actually start, let me tell you a little bit about why I got sparked to tell this story in the first place. So I'm on the Akka team for Lightband, and Akka is a library for the JVM to make it easier to build concurrent, distributed, resilient, message-driven applications. Well, that's a mouthful, but basically what it does is it introduces two basic building blocks, which are actors and streams. So maybe it's good to do a quick show of hands. How many of you are somewhat familiar with the actor model? Okay, so that's actually most of you. That's great. For those of you who aren't, then I'll highlight the important bits for this presentation, but I won't go into it itself. The second building block that Akka provides is streams. And streams actually look quite different from actors, but it makes sense for them to be in the same library because the streams can very nicely be built on top of actors. Okay, so these are fairly technical building blocks and relatively simple ones. The rest of the Akka library is useful tools on top of those to make actually useful applications. So we have an HTTP library, we have a persistence library which works really nicely well together with event sourcing. We have some clustering tools for nodes to find each other in a cluster, and that all fits really nicely together with the basic building blocks. So I've been working on Akka for a while, and one day I thought, okay, so Akka is built in Scala, and Scala is a fairly nice expressive programming language. And at one point I thought, why do we have a streaming library at all? I mean, why is this? I mean, from experience, it's nice to have it, but shouldn't this be something that we can express more directly in the language? And this was for me the starting point to say, okay, it might be nice to tell this story a little bit to show why it's useful to have a library and not build it from basic principles in the language. So this is the sort of the agenda for this talk. So I'll start by defining what streaming systems are for the purpose of this talk. I talk a little bit of different strategies, building it up from the really simple ways to implement streaming, seeing where they fall short and what you can do about it. Then we'll flow into Reactive Streams, which is a standardization effort for building streaming libraries. I'll go into some depth showing Akka Streams, which is our library that implements these concepts. I'll try to do a little live demo, so some live coding, and give some pointers where to look further. All right? So let's start with streaming systems. What does that mean for me today? And I think the main defining feature of a streaming system is that you process the workload, not all at once, but bit by bit. So you're not required to read the whole workload into memory first before you can do any applications on it, but you can do it like chunk by chunk. And the second characteristic is we want to process data as soon as it comes available to our application. So to sort of contrast this to big data, we like to call this fast data. So as soon as new information comes in, either produced by ourselves or coming in from some external source, we want to start processing it as far as possible without overloading backend systems. Also today I will be talking about streaming within one program. So of course such a program will exist in a wider application, so you will have different programs which stream to each other. Today we will look at strategies for building one such node. So things like Spark, which distribute a streaming job over a cluster, that's not what we're talking about today. Today is really about we're writing one application which has to do some interesting processing of some stream of data, and how do we manage that? I'll be sort of focusing on the JVM because that's where Akka runs. Of course, some of the concepts apply more broadly, but that's the focus for today. And what we're talking about is really not just getting bytes from A to B, so not streaming in the networking sense, but more streaming into, we want to do interesting operations. We want to split up our stream, merge things together, maybe parse something, change, interpret the elements that go to our streams. So what we're looking for is a sort of general framework in which we can do interesting operations on streaming data. Well, let's dive right in and start with like the most stupid simple streaming system you could have. So this is pseudocode. I try to keep it as simple as possible, not to distract with technical details. Here we read from an upstream. So upstream is where the data is coming from, and we write to a downstream. And what's notable here is that in this, of course, this is a mock toy program. The read call here waits until there's any data, and then the write call waits until the data can be presented to whatever target you have for your data. So there's an obvious problem with this approach. Can anyone dare to shout it out? I'm sorry, I didn't hear you. How do you know when the stream ends? Yeah, that's something I left out. So you could, well, there's several ways to do it. The thing I wanted to highlight with this example is because we're waiting for data becoming available to read, and we're waiting for room becoming available to write the data, we're blocking the thread of execution. And that's not so much of a problem if we just have one stream. Then we have one thread and we're fine. But if we want to do a lot of processing, we want to be able to have a lot of streams. And it gets really inefficient to allocate a whole thread for each single stream you want to support. So for instance, if your streaming system is in some places I/O bound, then most of these threads are actually doing nothing because they're waiting either for data to become available to read or room to become available to write, but we're still holding on to one thread. And especially on the JVM, threads are actually quite expensive. So a thread on the JVM has a counterpart in the operating system, so it's actually a native thread on the operating system. That comes with a stack on the operating system. It comes with load on the scheduler of the operating system. If you have lots of threads, then the scheduler has more work to do. And also at the JVM level, there's a stack which keeps objects which are on the stack in memory. So it puts an additional load on your the memory use of your system. Also, each thread is a route for the garbage collector. So anything that's reachable from a thread cannot be garbage collected. So this means if you have a lot of threads, then your garbage collector also has a lot of work to do, checking if which objects all those threads are holding on to. So okay, let's see what we can do to avoid blocking. So we discovered the first desirable property for streaming systems. We want to avoid blocking for each thread. So let's see what we can do. So most APIs, you can just flick a switch and say, okay, we don't want blocking. And we're doing this to the upstream now. So what this means in most APIs is that instead of waiting for data to be available, the read call just returns immediately with whatever data is in the buffer. If it's nothing, you get nothing. If there's data, then you get the data. Okay, this is fine. So you could think of like having a limited number of threads, just hitting all the different streams you have after each other. If there's nothing to be read, they finish quickly. But if there's something to be read, we're in trouble. Because we haven't made the write side non-blocking here. So this means those threads, if they have read something, now they still have to write. And if there's no space available to write to, then you will still be blocking the thread. So you will still be in trouble writing a scaling system. Okay, let's try it the other way around. Let's make the downstream non-blocking. Then we have to sort of move it on its head. We say, okay, now we're only going to read if we know there's space at downstream. Well, obvious problem here is now you know that downstream is ready, but now the read can block. If there's no data available, then you're still in trouble. Well, you can make them both non-blocking, but that also won't work. Because say you have read something, then you really must, you have this buffer, then you must write it. And so how can this return immediately? Because if there's no space to write it, then what do you do with the buffer? Okay, so the typical solution for this is we don't only have to be non-blocking, but we also have to change our programming models somewhat. So there's basically 3 ways to do non-blocking. The basic one we've seen so far is just flicking the non-blocking switch. Then the calls return immediately, but you're having trouble writing your actual stream. There's 2 techniques that are common for working in this way, and those are called asynchronous ways of programming, and this is with callbacks or with events. So the typical APIs who do non-blocking without just returning immediately is if you have a callback, you pass in the function that you want to be called as soon as data becomes available. In the case of events, is as soon as the data becomes available, an event is put on some kind of queue or mailbox. So of course these are sort of interchangeable, but if you're actually programming, then they look really different and they feel really different. So that's our second desirable property for streaming. We want our streaming to be asynchronous, so to decouple reading from writing. And of course, I'm an Akka guy, so the way I do asynchronous problem is with actors. So most of you are somewhat familiar with the actor system. I'll just highlight the interesting bit for this talk here. Is in an actor system, you can have many actors who do processing of messages. And the idea is that an actor is much cheaper than a thread. And each actor has a mailbox. And these actors can communicate by sending messages to each other. And sending messages to each other means putting messages into the actor mailboxes. And then there's a limited number, then there's a dispatcher. And the dispatcher, of course, there's still threads, right? I mean, computers work with threads. It's not like they disappear. They're just not so directly part of your programming model anymore. So the threads are managed by the dispatcher. And the dispatcher makes sure that it takes messages from the mailboxes and uses a thread to run them on that actor. And the important thing here is that each actor will process the messages sequentially. So the dispatcher will make sure that it doesn't pass 2 messages in parallel to the same actor. So this works really nicely because you can have a limited number of threads. Basically, if you're not avoiding blocking, you shouldn't have more threads than the number of CPUs, because what you're going to do with them. And this makes sure you can have, for a single actor, it sort of seems like you're in one thread because everything happens sequentially, but we don't pay the price of having a thread for each actor. So what can the actual processing look like? So this could be the implementation of our simple asynchronous actor. Messages come in, they are passed to us by the dispatchers, so we get a buffer. And what we do is the downstream, we send the buffer to the downstream with the bang operator. So the bang is the tell in Akka, which says send buff to downstream or put buff into the downstream mailbox.
So the bang is still blocking?
No, the bang is not blocking because it's not actually running code in downstream. It's just putting it in the downstream mailbox.
And that always has space.
Ha! So that's interesting. So I'm not sure if this was audible for everyone. So the question is, does the mailbox always have space? So this works fine if there's like the influx is sort of the same speed as the outflux. But if there's a lot more coming in than is going out, then you're in trouble. And typically, if you have unbounded mailboxes, then you get out-of-memory errors. So it sounded like a really good idea to decouple the downstream and the upstream. But if we do it without any further like safeguards, we're still in trouble. So what we see is we want our streams to be backpressured. So we want to have some mechanism to make sure if our downstream cannot keep up, that our upstream will avoid creating more work. And avoiding creating more work, of course, really depends on your system, what that means. So if you have just a generator, then you can just call it less often. If there's, for example, a TCP stream coming in, then you can actually tell the operating system, okay, I want to stop reading from this file descriptor now, and the TCP will do the windowing thing and tell actually the upstream system, like we don't have room in our buffers, yeah, you basically just have to wait. So let's get back to our first, most simple, most stupid example. It's interesting to notice that this most simple, stupid example actually had backpressure built in. Because if there was nothing in the downstream that there was no room in the downstream, it would just block here. And we would automatically avoid reading from the upstream. So that was kind of nice, but yeah, there were problems there. So that's why we end up with a little bit more complicated, but still manageable system, where sending stuff downstream is asynchronous, but we do need information channel that goes upstream as well. And this information channel basically just says, I have room for more. And downstream and upstream is both asynchronous, which avoids using a thread for each stream. And this leads to a really nice, flexible model, and also a pretty composable model. So is this clear so far?
Are you using the same case statement? Are you using the same method both ways?
In this example, I am. That's basically implementation, right? Yeah. Yes?
Where does the ready for one more come from, like an active supervisor or from like the downstream?
Yes, that would come from the downstream actor, because the downstream is the only one who knows whether there's more room downstream. So it depends on what you're streaming to. If you're streaming to TCP, then the information that there's room for more would come from the TCP socket. If it's something else, then you would need some other way to determine whether you have room for more.
They both arrive in the same mailbox then?
In this case, yes, but that's sort of an implementation detail, yeah. And the interesting thing is that it doesn't only work for like, because so far we've had like fairly stupid like one-to-one streams, but this actually composes pretty nicely. Because if you have a chain of a number of actors who all work this way, so you might have a filter and you might have a mapping, or you might have something that accumulates data until it sees a complete message and then interprets the message and sends that downstream. So you can think of more complicated stages that can still, by controlling how much ready for one more messages, this is of course pseudocode, it sends upstream, they control the end-to-end stream and make sure we avoid overloading ourselves. So for example, parallelism, it would be, in our most stupid example, we would read from the upstream, we would do our processing, and then write to the downstream. And that's really, if you have potentially a lot of things coming in, that could be really an inefficient way of doing things. Because once you've started processing the first message, maybe you can already start processing the second and the third message as well. Maybe you have enough space for this. So you can parallelize some of your stream processing. And so this approach with signaling demand upstream makes it really easy to make that possible. Because you just say downstream, you just say, okay, I have room for 15 messages. And then upstream, you can start processing 15 messages, and they can all go in parallel through your stream. They don't have to wait for your downstream to process the first message before accepting the second message upstream. So that makes for a really, a really flexible approach where you can make a complicated graph, and this downstream demand just bubbles up through the graph.
How do you determine the size of the buffer that you have for the actor? Because if you have a lot of actors, you might have a lot of coordination, signaling demand.
Mm-hmm.
Do you offer tools to help with that? Or
Yeah, so the question is, what if you have a lot of different streams? And if I'm paraphrasing correctly, if you have a lot of different streams and they're all signaling demand, is it useful to have some sort of coordination between the streams that they're not signaling demand all at the same time? Yeah. So we don't really currently offer anything for this. So because usually it's enough to make sure a stream doesn't completely overload itself, and you have some kind of tuning you can do to determine what your workload typically needs. What you can, of course, do is create systems where you have streams of streams, where you avoid creating new streams when there's too many streams already in progress. So if you have some kind of metrics on how many streams you can have in parallel, then that can be a solution. So to recap again, we basically discovered 3 desirable properties for streaming systems. We would like them to be non-blocking. We would like them to be asynchronous to manage that non-blocking in the best way. And we would like them to be back-pressured to avoid overloading our downstream stages. And this brings me to the Reactive Streams initiative. So circa 2013, a couple of people from industry got together and decided and kind of discovered that they were solving the same problem. And so this was from Akka, from RxJava, and some Twitter people. And they were all struggling with the same problem and finding solutions. But these solutions were not very uniform and not very interoperable. The idea was born to see if they could find a common interface so they could solve this problem in a more uniform way. And also be interoperable, so have the back pressure actually flow from one library to another. So this started the Reactive Streams expert group, and at some point, basically the main deliverable delivered by this expert group. Sorry, let's start with the scope of the Reactive Streams initiative. So this was an initiative to provide a standard for asynchronous stream processing with non-blocking back pressure. So basically the exact 3 characteristics that we discovered, those were at the core of the Reactive Streams initiative. So the main deliverable of this initiative was these 4 interfaces. And as you can see in the subscription, this request is basically corresponds to the I'm ready, the downstream telling the upstream, I'm ready for more data. So this is an asynchronous call which just tells the upstream I'm ready for more, but does not do anything on that same thread. So the rest of this is kind of some extra things to make error handling and detecting when the stream is done possible. So how many of you are programmers, would identify as programmers? Okay, that's most of you. So I know how I'm a programmer. I know how I think. When I see 4 interfaces, I think, yeah, I can do that. Just let's start coding, right? But these 4 interfaces are not the only deliverable of the working group, because to make these libraries properly interoperable, there's actually quite a bit of subtle rules you have to implement correctly to make it actually work end-to-end. So each of these interfaces has something like 11 to 17 requirements that go with those interfaces. And it's not so simple to create a program that actually correctly implements all these interfaces. There is a TCK that can help you to check your implementation, but really these interfaces are meant for library authors. So if you're programming an application, an something that does something useful, you wouldn't deal with these interfaces directly. You would use RxJava or Akka Streams or a library like that to build your streams, and the library will take care of adhering to all the specifications. So one of the libraries that does this is Akka Streams, and I'm going to do a little overview of what Akka Streams roughly looks like. So the basic concepts of Akka Streams are sources, flows, and sinks. So a source is something where data comes out. A flow is something where data comes in and data goes out. And a sink is something data goes into it and is gone. So let's give some examples of sources and sinks. These are in Java. So you can have, yes?
Java has a few types of sources. For example, single maybe. Akka Streams that doesn't have something similar. Because in Java, for example, single is stream which produces just one. Maybe is stream which produces 0 or 1 values.
Yeah.
And it helps to when you have to make some semantic of your code, and source does Akka has something similar?
Yes and no. So Akka definitely has source.single to create a source that has a single element. So you can easily do that. But after you made it, it's just a source. So it's not visible in the type anymore.
Okay, so some function, for example, returns some string, so we don't know how many elements the string can produce.
Correct. So such a function would, if you want to provide a function with, which produces 0 or 1 element, it might be easier to just return a future.
Okay.
And if you want something that can handle both, then you can return a source. But as the consumer, you can't really see if it's a source which only produces 1 element or an arbitrary number.
Okay.
But, so if you want to have it visible in the types, then using futures is we think is a nicer way to encode it.
Okay, thank you.
Yep. So we can take a function and create a flow out of it. And we can create, for example, a sink that just prints everything. So if we also show the types, I think looking at the time, maybe it's not so interesting to look at the types too much. It looks pretty much the same in Scala, which is what is nice both in Java and Scala. This is all type checked. Okay, so that's maybe an interesting thing to see at the types. Is a source is not just a source, but it is a source of integers. a flow goes from integer to string. And of course, you cannot make connections which do not make sense.
Sorry,
Yep.
what is not used type?
The not used type is basically just unit, so it's just a type with just one element. But it's used here to explicitly say a runnable graph can have a result, but this particular runnable graph does not have a result.
Okay.
So that's what we use this type for. So the syntax I showed before was a little bit verbose, which shows how you can nicely compose streams. But if you just want to write a stream, a self-contained stream, then there's convenient combinator methods to just write it all in one line. I'm going to skip materialization, and I'm going to show a tiny little demo. So the demo I'm going to show is a TCP server. Is this readable? Okay. I don't remember how to make it back. Oh, I guess I can show the... Okay, this doesn't help a lot. So I made a tiny little TCP server. So it binds to localhost on port 8081. And what this binding produces is a source of incoming connections. And then we want to run this source of incoming connections. And for each connection, we handle it with a flow. So remember, a flow is something that on the one side things come in and on the other side things go out. So a connection is kind of, you can handle it with a flow because this flow, the incoming data goes in and whatever comes out of the flow we send to the network back to the client. So in our particular case, we just created a flow from a sink and a source. Actually, we just ignore anything that comes in, we don't care. But we produce on the output, we produce just numbers, we throttle it a bit, and we turn them into byte strings because the TCP connection expects byte strings and not integers. So let's see if we can run this. And at the same time, we will run SS. And SS is a Linux tool to show the current TCP connections. And what's especially interesting in this case is the receive queue and the send queue. These are the operating system queues holding any data which is being received or being sent to the other side. So I've started the application. Now we can connect on port 8081, and we see the numbers. We also see the connections here. And I can suspend our netcut command. So we stop consuming from the TCP connection. And we see first the receive queue gets bigger and bigger because the operating system receives the data, but we suspended a netcut, so it's not actually passed to the application anymore. And after a while, we also see the send queue increase for the application. And the nice thing about having back pressure all the way is that the fact that this send queue is now increasing also means that the Akka Streams will stop sending demand upstream. So it will actually cause in our case, it's just a mock source which just produces numbers, but whatever is producing data to stop producing data until we continue reading, and then you'll see the queues go to 0 again. So that's really And this is really all there is to it. I mean, this application contains nothing except this class, a dependency on Akka Streams. That's it. So with that, I want to start wrapping up. So of course, Akka Streams is not the end-all and be-all of streaming. There's lots of other interesting ways to do it. In the Scala ecosystem, FS2 and Monix are really interesting approaches. There's interesting things going on in the JVM land. So Project Loom is working on fibers, which should be lightweight threads. That's really exciting. It's not super clear how it's going to work out and how lightweight will lightweight be in practice. So, but that will be super interesting. And of course, beyond the JVM, other languages are taking radically different approaches to this kind of thing. So that's super interesting. We have a little time for maybe a couple of questions. Yeah, let's just take one maybe. Yeah.
Hello. So in your introduction, you promised that you would tell us why this is a good fit for a library and not a language level thing. So can you clarify that?
So what I hope I showed is that it's just tricky enough to not have to do it again each time you write a program. So because you think, okay, Scala is an expressive language, why can I not just express this in the language? Well, of course you can, but it's to make it work actually nicely, there's enough, maybe accidental, but there's enough complexity coming in that you want to hide that complexity in some exceptions that come for a library. Of course, you could put things like this in the standard library, but that doesn't really change the
I just misunderstood you. I thought the point you want to make is language versus libraries, but you're making the point libraries versus applications.
Yes, yes. All right, well, I think it's good to wrap up by now. I want to do one last pitch before we really stop. If you're a Scala programmer and you are a participant of an open source project, or you would like to be a participant in an open source project, ING is hosting a Scala spree organized by the Scala Center. I will be there for the Akka project. If you're interested in this, should be a lot of fun. Find it online and see us tomorrow. And with that, I'd like to thank you for your attention.